Our last lesson for this year is going to be on using fundamental trigonometric identities. We've already talked about the fact that the reciprocals of the trig identities for sine is the reciprocal of cosecant, cosine is the reciprocal of secant, tangent is the reciprocal of cotangent, and then it's basically vice versa. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent. And we've also talked about the fact that tangent is sine divided by cosine when we learned how to make the chart. Well, since cotangent is its reciprocal, if you just flip that over and make it cosine over sine, that's equal to cotangent. These other three identities we haven't really talked about too much, but they all relate back to the Pythagorean theorem and the fact that on the unit circle, the sine is the y-coordinate of a point on the unit circle, and the cosine is the x-coordinate of a point unit circle, and the radius of the unit circle is 1. So sine squared plus cosine squared equals 1. That's probably the one trig identity most students remember years later, or maybe. Anyway, 1 plus tangent squared of x is equal to secant squared of x, and similarly, 1 plus cotangent squared of x is equal to cosecant squared of x. So we also have some other identities, which we also talked about earlier, the cofunction identities. The two functions that are cos of each other, like sine and cosine, tangent and cotangent, secant and cosecant, they're called that because co is the same two letters that complement starts with. So the sine of an angle is the same as the cosine of the complement of that angle. And when we're in degrees, that would be 90 minus the angle, but in radians, it would be pi over 2 minus the angle. Same with tangent. The tangent of an angle is the cotangent of its complement. The secant of an angle is the cosecant of its complement, and those also work in reverse. Odd-even identities tell you whether a function is odd or even. A function is even when, if you plug in negative x and simplify it, you get the same thing you got by plugging x in. So cosine is an even function, and so is its reciprocal secant, because the cosine of negative x is the same as the cosine of x. But sine and its reciprocal cosecant and tangent and its reciprocal cotangent are odd functions, because if you plug negative x into the function, you get the opposite value than you got when you plugged in positive x. So looking at this triangle and thinking about the cofunction identities, angle A and angle C are complements of each other. If we're thinking about angle A, which I have marked in red here, BC would be the opposite, and this would be the hypotenuse. If we're talking about angle C, AB would be the opposite, and the purple one would be the hypotenuse. So the sine of angle A would be this opposite over hypotenuse, BC over this. The cosine of angle C would be the adjacent, which is the same BC, over the hypotenuse. So that's why the cofunction properties work when the two angles are complements of each other. It's like they're the two acute angles within a right triangle. So the way we're going to use these is to simplify trigonometric expressions to try to make them simpler to work with. And the thing that's true from, you learned it way before, but in geometry you really put a name to the fact that if two things are equal, then you can replace one of them with the other one in any expression or equation. And this is called the substitution property. So if I see an expression that looks like this, and I want to simplify it, well, one way to simplify it is to try to get it to just have one trig function in it instead of two. Another way to simplify it might be to factor it. I notice that these two terms have a common factor of sine. So if I take out sine of x from the two terms, in the parentheses I'm left with cosine squared of x minus 1. Now, if you think back to your identities, there was an identity that related the sine squared and the cosine squared. sine squared plus cosine squared equals 1. So sometimes you have to make things more complicated to make them simpler. This plain sine of x I'm going to leave alone, and I'm going to leave the cosine squared of x. But I'm going to replace the 1 in parentheses with sine squared of x plus cosine squared of x. I would distribute the negative through here, so both of those terms are now negative. This cosine squared of x would cancel with this cosine squared of x, and now this sine of x is multiplied by a negative sine squared of x, which means this expression that we originally had is equivalent to negative sine cubed of x. And that looks quite a bit simpler than the original expression. It only has one term and it only has one trig function. Many times factoring something can help you simplify it. So for example, in this case, this kind of looks quadratic to me, except instead of just a variable being squared, it's a trig function that's squared. So if I treat that variable, that tangent of theta, as a variable, I'm just going to say, okay, I'm treating tangent theta as x. So I'm going to rewrite this as 4x squared plus x minus 3 equals 0. Well, that trig function, that quadratic equation, I think is fairly easy to factor. Let's see, we need the products to subtract to give us 1. Factors of 4 are either 4 and 1 or 2 and 2. Factors of 3 are only 3 and 1. Over here I'm going to put 1 and 4 so I get both orders. And I need the products to subtract to give me 1. Well, 1 times 3 is 3, 1 times 4 is 4. When I subtract those I get 1. So that means my parentheses are going to start with 1x and 4x. And they're going to end with a 3 and 1, but the 1 has to be multiplied by the 3, so the 3 has to be over here, and the 4 has to be multiplied by the 1, so the 1 has to be there. The minus here tells you they have different signs, and this tells you the bigger product has to be positive. So the 4 was the bigger product, so I have to put plus here and minus here. Well, now I have a product that's equal to 0, so I can say either the first thing equals 0, or the second thing equals 0, and solve for x. So here I'd subtract 1, and I get x equals negative 1. Here I would add 3 to get 4x equals 3, and then I would divide by 4 to get x equals 3/4. But remember, it wasn't x. X was tangent